This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right. Okay, so if you didn't see the announcement on LMS, the specs for the project part of the subject, so getting your kabuki to go over the obstacle course, around the obstacle course, up and down a ramp, on LMS. Okay, so go and check them out. This lecture is a really interesting one because it asks the question as to what two embedded systems can be considered equivalent or the same. Okay, and we're going to call this equivalence, obviously, and also refinement, that a machine can do a subset, for instance, of activities that another machine can do. That might be important when, say, you want to compare your FSM for your kabuki navigation and hill climb operation to maybe your friend's one who's in another group, and you want to see if they do equivalent things. You'll learn the techniques today where if you have a complete FSM description of both of those behaviours, you can then prove whether or not they're equivalent. Okay? So, if you had a system like this, the MyRio board here, and with a Cortex-A9 chip on there, could you just simply desolder the thing and just throw on a Cortex-A12? Now, the first thing that you might have to think of is obviously the pins have to line up. You've got to have the same amount of pins. Perhaps they've got to be the same voltage ratings, current ratings, or input-output clocks, whatever. Okay, but assuming all that lines up, would it work? Okay, well, this is a question which you can't normally just throw something together and try it, because if it's a mission critical situation, you can't go and drop a new processor inside some system where you can't, say, remove the whole board, where as soon as you power it on, it's going to power a nuclear power plant or something like that. It's supercritical. Actually, supercritical is probably the wrong word to describe a nuclear power plant. But to it's a situation where you can't just hack and slash things, okay? You've actually got to formally prove that what you're going to do is going to work. So we're going to look at this, but restricting it to comparing not microprocessors, but state machines, because we have a formalism for describing how state machines work. And why do we need to compare them? Well, if we're given a specification for a state machine, we need to check that our state machine actually conforms with that specification. If it doesn't, well, you haven't done a good job, right? You haven't built it according to the specs. Then again, if you've got an FSM and you've got another FSM that has reduced complexity, maybe the state space that it occupies is much smaller, therefore it's cheaper to implement in hardware, you might want to check that those two machines do the same thing. And as I said just before, you might want to check that you can substitute particular components. Oops, clicked on the wrong thing. Okay, so an equivalent component you can swap and the machine overall will behave exactly as expected. So how do you compare the two machines? We're going to look at two notions today. One's called equivalence, and the question that can be asked is, do the two machines do exactly the same thing? There's some subtle things we have to cover there. And then refinement. And that is, does one machine do a bit more than the other? So maybe it's got a more complex operation, it can do more, but it does enough to satisfy what another machine does. Okay, so we want to be looking at whether or not machines can exhibit different behaviours. So one may have a subset of behaviours of the other one, and also whether or not the outputs are different in terms of its input-output behaviour. Okay, so I'm motivated by using a really simple FSM, a pretend one for the Kabuki. So there's the Kabuki there. It's a two-state FSM. You should be already looking at that and knowing exactly how to describe it. It looks deterministic. Okay, we've got level, we've got not level. Looks good. It's got two outputs, pure outputs, forward and rotate. So it's a very simple state machine. All it does is, if level input's present, it drives forwards by issuing a drive command going forwards. Then if the level input's absent, it just does a rotation for a fixed amount of time. Okay, so it's a very simple two-state machine. So we could abstract that state machine a little bit. Remember, state machines are almost arbitrary in how you choose your states. Sometimes you start off with a lot of states and you refine them down to next to nothing. And indeed, here is a very, very simple state machine. It's just a one-state state machine called driving. The state is driving. And we want to know whether or not this state machine, or this FSM, is equivalent to the one at the top there. And what do we mean by equivalent? We're going to mean three things. For deterministic machines, it's really two. The last two combine into one thing. Okay? So, are they equivalent? The first thing you have to check in my little example before replacing that chip on the board is that the pins match up, basically. In the more abstract notation of FSMs, if the input-output spaces line up. And in this case here, so the actor models for these machines, so they've got the inputs and the outputs, and we've got to specify the types of the inputs and outputs. So they have the same input ports, they're actually even the same names, and they are the same types. So it means from a black box perspective, this looks exactly the same, right? And this is what's known as type equivalence. And this is almost a trivial one. It's, funnily enough, it's the one that sometimes gets a lot of people into trouble because they get very hung up on examining the behaviour of two systems and they forget about type equivalence. A classic case was a case where in industry, it would actually cost hundreds of millions of dollars, this issue, where some design teams were working away and, you know, you modularise a project, you each work on the modules, and the two modules got put together and they didn't check type equivalence, well, between the two models. Essentially, two of the pins were flipped on one of the units and they put them together and the whole thing went up in a rather nasty accident. So, and that's simple. That was just checking type equivalence across, you know, two different FSMs put together. Okay, that's the easy one. Make sure the ports have the same types, and then you can obviously do a substitution for M1 and M2, these two FSMs. That's easy. So good, we can tick that, they're type equivalent. The next type of equivalence we're going to look at is called language equivalence. And once again, just confining ourselves to this little example here, what we're going to look at is for every input sequence that we get, the two machines are going to have the same output sequence. So once again, think about a black box. You probe the black box with some inputs, some outputs come out. You probe the other black box with some inputs, some outputs come out. You compare the two and they're identical. That's it. This is called language equivalence. And indeed, you can check, oops, my cursor. So indeed, you can check, right, that condensing these two states into the one state is fine, where we have these two stuttering transitions here, but they alternate the outputs based on what level is doing. Okay? So we don't really need that concept of state. This is better for readability, perhaps. You can really see, and because they're named, it might make a bit more sense. Here, it's a bit more abstract as to what's going on. You've got to read into what these transitions mean. Okay, that's language equivalence. That's the second part of equivalence. So we've got type equivalence, language equivalence, and this is the very subtle one called bisimulation. Now, it's not just simulation, it's bisimulation. What do we mean by bi? Well, bi means obviously left to right, right to left. So it means that M1 simulates M2 and M2 simulates M1. So it goes in both directions. And doesn't this just mean the same as input-output behaviour? So if I want to simulate something and I look at the black box, isn't that the same thing, right? Input-output behaviour, that's language equivalence. But isn't that simulation? And indeed, if you read the description here, it's almost exactly the same. It turns out that because these two machines here are deterministic machines, language equivalence and biosimilarity are the same. They're exactly the same. But for non-deterministic machines, they're not the same. It actually comes down to a game of who goes first, if you like. Because if we think of non-deterministic machines as having multiple options for transitions out of a state, it gets a bit tricky. And we're going to play that game a little bit later on. But for our little example here, there are three types of equivalence that have been matched. Well, really two, because it's a deterministic, both are deterministic machines. So biosimilarity is the same as language equivalence. So yes, we could swap those two machines in and out, and we would consider them being equivalent, and they should work exactly the same way. Hardware-wise, internally, there's different implementation of these. Okay, more states means more memory, flip-flops, whatever you want in there. All right, so so we could still have two machines, M1 and M2, that are not equivalent. They don't satisfy those three exact things for the Kabuki example before of type equivalence, language equivalence, and biosimilarity. So we have three different things to look at. We have refinements. So where they're not precisely the same, but there's kind of like they can do subsets of each other's things, almost. Okay? Refinement's almost like the opposite of abstraction. Where abstraction, we lose stuff. Sometimes, well, refinement, we can have a more rich model. But it can still do the same thing as an abstracted, simplified model. Okay, so three definitions here about refinement. So let's say we've got a machine M2. We say if it's type compatible with M1, so we can swap it over, we call that a type refinement. And we'll see it doesn't have to have the same amount of inputs and outputs, okay, for a refinement. For equivalence, yeah, exactly the same. M2, this other machine, could be a specialisation of M1, such that it can only produce output sequence that M1 can produce, given the same input sequences. So it's like, you know, it can only produce that sequence. And we call that a language containment. We'll go into more detail about that in a minute. And lastly, simulation is that M2 being a specialisation of M1, machine M1, in that at every action, M2 can produce only output values that M1 can produce. And we say in this case that M1 simulates M2. So what do we mean by a valid situation? So we've got M1 and M2, and perhaps we wanted to swap one for the other. When would it be valid to do so? This concept of what valid means is a bit rubbery. We can mould it around a bit. It depends on what the meaning of valid is. And depending on if it's a type, language, or simulation refinement. Okay, it could be valid if it's just a type refinement. That's it. It doesn't have to necessarily match the exact input-output behaviour. It's just a valid replacement for something. Okay, and we're going to say that M2 implements M1 if M1 is some specification. Okay, so I might give an example, for instance. So if M1 was a specification, specification might be English specification, maybe me to get to the other side of the table here. Okay, there's one way of doing it. That was 5 steps, right? But if I take bigger strides, right, there might only be 2 states. If you think of a step as a state, same output was achieved, but there was 2 states versus 5. Okay, so different machines have implemented the same outcome. The spec is met, but the process of doing it is very different. All right, so let's look at refinement. Type refinement, type 1, this first bit. So it was very trivial when you just looked at that Kabuki example. Yeah, same input, same output, swap it in, fits exactly, same profile, the chip's exactly the same. But we're going to be a bit more formal about it. So here's machine M1. It has inputs X and W that live in, that come from spaces Vx, Vw. Okay, they could be real numbers, they could be natural numbers, whatever, present, absent, whatever they are. And P1 is the set of these input signals. Remember, this is how we are characterising our FSMs in this formal set notation. Has output Y, lives in space Vy, and the overall spaces of outputs is just, the set of outputs is just Y. So let's say we had another machine, M2, that has only a space of input, a set of inputs X, where it belongs to now this new Vx prime, and additional outputs Z that belong to Vz prime, and the set of outputs is now Yz. So it's got additional outputs but a restricted amount of inputs. And we say that M2 here is a type refinement of M1 under certain conditions. Now, one of the conditions I think is fairly obvious, and one is a bit, you think, okay, that's interesting. The conditions that I'm going to talk about are here and here. So if P2, so the input space of machine, the input set of machine 2 here is contained in the set of P1. Okay, so in this case, clearly this is the case, right? So X is a subset of P1. Well, P2 is a subset of P1. So think of that as it doesn't necessarily have to react to all the inputs. Okay, that's reasonable. Can ignore some. That's fine. On the output side, you can actually, for M2, you could have additional outputs here such that the output set of the original M1 is contained in the output set of M2. What does that mean? Think about swapping those squares into a circuit even, connecting them up. If I drop this into the place of this, it's all good. These outputs would just be ignored by the environment. Okay, you can imagine this is going off to some other things, whatever it goes to. And if I drop this in here, sure, these things are connected, but any additional outputs here would just be ignored. That's all right. You can have more outputs here. So if all of these conditions are met here, for all P and P2 and all P and Q1, etc., then M2 can replace M1. Copy, paste, drop it in, and you won't have any type issues, type conflicts. Okay, so that's the formal definition of type refinement. Once again, it's simple to comprehend. It's something that people tend to forget because they get hung up more looking at the behaviour of the machines and comparing actual input-output behaviour rather than checking that the ports are actually okay. All right, so just to give you an example, the garage counter we looked at was that simple counter that just ticks up or down depending on if a car comes in or car goes out, and will indicate how many cars are in the space. So it is a very simple state machine. It has a ticker, or a counter up or down, detecting cars entering or leaving. And it has an output port Q that is of type V count. It's a natural number, right? It's going to spit out some number that will go to a display somewhere. So this state here actually holds the amount of cars that have come in, right? So up is present, down is present, etc., right? You can count up and down the chain. So a behaviour of this, so if we look at a sequences of inputs over time and have a look at the output, the sequence of output over time, anytime, for instance, we have up and down both present, the count remains the same. We have both absent, well, the count is absent. We have a car enter, goes up, goes to 1, car leaves, goes to 0, car comes in, goes to 1, etc. So you can see the sequences here. The sequence is either natural number here or absent actually as well. Okay, so that's our little garage counter for some number M, where M is maybe the amount of spaces that are available in there. You want to count up to that number. So suppose that's M1. Let's call that machine M1. Suppose we've got another machine, M2, that now has M, the amount of spaces, restricted to 90. Or the amount of cars it can count is 90. So it's only got 91 states, actually, funnily enough. It'll be 91 because I've got to add to 0. M2 is a type refinement of M1. Clearly is. Right? Think about inputs, outputs. It's got exactly the same structure to the inputs and outputs, so we could just drop it straight in. But internally, it's got a different amount of states. So the question is, would it be all right? Is it okay to just drop a new one in there? The answer is it depends, right? Obviously, if you drop that into the system there and you get 91 cars come in, then you've got a problem, right? It can't count beyond that, so it's going to lie. It's going to saturate at 90. So it's got similar behaviour. It's a type refinement, so it works. It's type equivalent, actually. It'll completely work in there, but internally it's not valid for the particular setup there. So it's not always okay. It might be okay if perhaps you were using M1 with 99 spaces and it was only a 60-space car park. Okay, you could drop M2 in there, no problems, right? Because it still counts to 90, which is more than what you need. All right, so we could also swap the machine, or condense it, I should say, down to one of these single state machines again. And we saw this in an earlier lecture. So instead of actually holding the state as the output as the state, you could actually encode, in a funny way, the state in a variable is an extended state machine. So you basically pull in a little internal variable, call it C, and that is keeping track of the count as you go. And therefore you don't need independent states to keep track of the count. So we can replace it by this equivalent machine here. It's got the same I/O, but it has a very different state space, if you like, compared to the other one here. Okay. So we keep talking about what machines are equivalent. These two machines of the Kabuki here are considered equivalent. We saw they satisfied 3 conditions for equivalence. For deterministic machines, we look at language refinement to specify whether or not they're equivalent. That's looking at input-output behaviour. And for non-deterministic machines, we have to go to simulation, and in particular bisimulation. And that's going to get a bit of fun because we're going to play this ordering game. All right. So remember what an execution trace of a state machine was. it's a sequence where each step, so we title these as queues, and each queue is a combination of all of the inputs, outputs, and the state at a particular step. And there's a nice way of writing this, particularly for smaller state machines where you don't have to go over the top in terms of the amount of inputs and outputs, as a little arrow transition. So here we're in S0, and for input X0, we output Y0, and we transition to S1, etc. So we put our inputs and our outputs, our transition guards and our outputs here like this. So it's like a flattened FSM almost for a particular input case, I should say. And for deterministic machines, this is a beautiful, just a long straight line, because we don't have multiple paths we can take, right? We get a tree structure when we have to think about non-deterministic machines because we're alternatives to take, and we branch out. So that's one way of characterising the behaviour of a machine, right? Clearly, we can watch its state evolution and we can see its input-output sequence. Now, we're not going to worry about the S's so much, okay? If we're looking at language refinement, we want to look at the machine as a black box, right? We don't care necessarily how many states it has or anything. We will only look at input-output behaviour. Okay, so I don't care if it has 100 states, 1,000 states, as long as for a given input sequence, it gives me the same output sequence there. Okay, so we're going to not focus in on the state here. So we're only comprising inputs and outputs. And remember that the behaviour of a machine, so this is a bit of a rehash of before, the behaviour of an FSM is the set of all possible traces that you can get. Okay, so think of all the possible input sequences you can put and all the possible output sequences you get, and the big family of all that, that's the behaviour of the machine. Okay, so thinking up the order, trace is output sequence for a specific input sequence, and you put the state in there. Behaviour is now the set of all of those possible things. So it's a bigger family of things. That's what all that stuff says there. It's stuff we've seen before. But here's where it gets interesting. We're going to define the language of a state machine as the set of all behaviours of that machine. Okay, so we're stepping out even more, if you like. Now, so let's look at a couple of machines again. M1, M2. We've got inputs in their spaces, outputs in their spaces there. We're going to assume that they're type equivalent machines. Okay, when we delve into language refinement, we want to check that their input-output behaviour matches. It doesn't make sense to not have them type equivalent, right? Because we're looking at input-output behaviour. They better be type equivalent. Okay, so if they're type equivalent machines, M2, so this guy, think of this guy here, is what's called a language refinement if the language of M2 is contained in the language of M1. It's a subset of. So we can draw that nicely. Once you think of subsets and all that stuff, you can think of Venn diagrams or whatever, and you can see that here, the language of M2, so the set of all possible behaviours here for M2 is a subset of all the possible behaviours of M1. Okay? In other words, you might like thinking of, so M2 can replace M1 for input-output sequences of interest, if you like, okay, because it's a subset. Let's do some stuff in some more concrete examples. So let's look at two very, very simple state machines. M1, M2, simple inputs, scalar inputs, x, y, pure input, output. So immediately those two machines tick, type equivalent. Look at those inputs and outputs. They're named the same even. So perfect, type equivalent. Are these machines language equivalent? In other words, input-output behaviour, the same for these machines. Okay, are they the same? They are, right? So if x is present, so x is present for all of these things here, so the sequences here could be O1, O0, and this machine here, M2, seems as though it can replicate that sequence, right? O1, O0, O1, O0, right, of all the possibilities that could occur. So they are language equivalent. But there's something interesting that's going to come up here, in particularly that this non-determinism here, and here as well, is going to mean that they're not, so they're language equivalent, but they're not, they can't completely be swapped with each other, if you like. All right, how so? There is a context. So you might think, okay, clearly type equivalent, language equivalent, let's swap them over. But there's a special context where M1 cannot be replaced by M2, right? And it's because there's non-determinism. That's why. Right? Remember, when they're deterministic machines, language equivalence is the same as bisimulation. Tick, all three ticks, all good. Here, not so. Okay, so let's investigate this a little further. Let's pretend M1 is the specification. It does everything okay. That's the spec. Everything it does is okay. Now, it's fine to replace this machine here with this machine M2 because at each step in the sequence here, or transitioning through here, any move that M2 can make is also okay, because any move that M1 can make is okay. All right, what does that mean? Let's trace through this. Clearly, right, if x is present, the output's 0, right, and we can replicate that either way here, right? Seems as though, okay, yep, sure, we can replicate that. And if x is present, we can go 1 or 0. We can go 1, or we could go 0, or it seems, well, it seems like it can, right? Because at each step, any move that M2 can make, any move is okay with any move that M1 can make. But if we flip it around a bit, and I might draw out this one to show you a little more. Let's see what happens when we pretend that this is the specification here now. So here's the spec, and we want to replace it with M1. Now, one way of thinking about this is, let's pretend that M1 is a malicious machine. Okay? So it's going to watch what M2 can do, and it's going to try and screw us up. Right? Why not? So, for instance, now I better make sure I get my sequences right here. Yeah, easy. So, for instance, let's say that this transitions through. So M1 can see what M2 is doing, if you like. So here we've got a choice to make. It's non-deterministic. It'll go one way or the other. Let's say it goes, I don't know, it goes to F perhaps here, right? So this machine has no choice. X is present. It's got to go this way, yeah? It has to. It's deterministic, that transition. Now, here we've only got a deterministic transition, so it goes through to here. But in this machine here, well, the output was 1 for this machine, but I've seen it's that, so I'm actually going to choose this one instead. So we get a contradiction, right? A clear contradiction in terms of the output for this guy has been 1, but the output for this one has been, 0, and the output for this has been 1. So once again, think about M1 as almost looking at what M2's done and choosing the opposite. And so you can see it doesn't work in this case. Here, if M1 is the specification, so let M2 mirror M1, even if it tries to do it maliciously, it can't do that. It'll always be locked into the same input-output sequence. It's probably a better way of saying it. Okay, and we call this the matching game. Now, there's a formal way of proving this. And the formal way of proving this is by constructing what's called a simulation relation. So let's code up all the states for our machine 1. There's 4 states. There's 5 states in S2. That's okay. We can still have language equivalents with different amount of states. We saw that with the Kabuki model, right? 2 states versus 1 state. They don't have to have the same states. Now, what we're going to do is we're going to see if M1 simulates M2. Okay, so I think I've got the animations yet. What we're going to do first here is, so this is what we're going to call, it's called the matching game. And I kind of, I hinted at it when we looked at this being the spec and then the other machine maliciously trying not to do what the other machine has done on transitions, okay? So what we're going to do here is we're going to create a set of the joint states of the system, of the combined system. Remember, this is not 2 machines composed together. This is a set that's kind of looking at the equivalence of the machines, okay? It's not combining, it's not concurrent composition. It's just looking at the 2 together. So let's start the game. Let's pretend that each machine starts in its initial state, and we're going to make M2 move first. Remember, when there's non-deterministic stuff, we're going to choose which machine is going to actually make the decision before the other one. So let's make M2 move first. So here we go. So we start off in this. So we're going to combine these into a joint state. That's the cross of the 2 spaces of both of the states, the sets of the states. All right. So the first possibility, well, this only has one possibility, right? If X is present, it has to go to B. But this guy here can either go to F or H. So the first possibility, if we take that up, a transition, because it's non-deterministic, we get the tuple FB as the joint simulation, the set of states in the simulation relation. But the other possibility that we could have had clearly was if instead of going E to F, we went E to H. So therefore, we also have the possibility of this joint state, if you like, HB. All right, and then we've got to cover the other possibilities. So moving this in the green and moving in the blue here. So, for instance, which one's the first one? So green is the first. So if X is present, and we were in FB, remember? So we've almost got to backtrack a bit here. X is present, we go to GC. Notice how we're ordering these as well. These are ordered based on who's moving first when we're analysing these. So M2 states are coming first. It's a nice way of remembering which one is actually we're determining goes first. And we go through, again, at this state here, we can go down to the blue here, go from H to I and B to D, so we end up with ID here. And this is our simulation, and then that's it. We've covered all states, all transitions. We're at the end of the chain, so to speak here. We've covered all possibilities. Okay, we've had no contradictions. While we're doing that, we're actually checking for contradictions in outputs as well, okay, as we've been going. Because we can't have a joint state here where it's in state H and state B, where H has an output, what's the output? Y is 0 and B has it as 1. We can't have that contradiction because then they're not equivalent in that sense. All right, so we've constructed this and we've found no contradiction in terms of the output. That's it. So we can safely say that I think that comes up. Yeah, so we can safely say that M1 simulates M2. Okay, so M2, remember, back on this slide here, M2 was moving first. Okay, M2 was moving first. And M1, so therefore M1 has simulated it. We could say M2 refines it, or M2 can replace M1 everywhere M1 is okay. Now let's look at the converse. Let's flip it around. Let's see if M2 simulates M1. So in this case, what we're going to do first is M1 is going to move first. These are non-deterministic, so M1's going to move first. So I'm going to order the simulation set here of states with M1 as the first element. Just keep track of it. Okay, same thing again. Here we've got a deterministic transition. We've got to do that. And F, there's a valid choice going this way for up to F. Now, here we've got two choices. And it's going to lead us down to a path that's going to make us very angry. Very angry. Because if X is present here, well, we could clearly go to D. So we could write D, underneath him, write D. And we only got one way to go here, right, to G. Now, what's so bad about that state that makes this face super angry is that the outputs here are incompatible, right? This transition has enabled Y to be 0. This transition has enabled Y to be 1. So we don't have corresponding output behaviour. Interesting. So it's like it's a one-way street here, right? That M1 can simulate M2, but M2 does not simulate M1. Okay, and it's because of this non-determinism, right? We saw that input-output behaviour looked all right, didn't it, right? It can replicate the pattern 0, 1, 0, 0, 0, 1, 0, 0. Sure, it can do it. But in terms of looking through the traces here, it doesn't. The outputs don't match. So the game here, the matching game is to start one... the game here is to make one of the machines move first and then build up this simulation relation, check for incompatible outputs, flip them around, start the other machine moving first, always, and then build up the simulation relation, check the output to make sure that they're compatible. And it turns out, if you think about it this way, that when you postpone decisions, it's more powerful than not. So what does that mean? There's a nice dot point underneath that. Free will is more powerful than preordination. That's a nice little idiom there, I guess. Remember that you have free will, if you like. The non-deterministic machines have free will of choosing, in this case, one of two possible states here. Here, you've only got preordination based on the guard evaluated it true to go one way. Okay? So in this case, once again, M1 can do anything that M2 can do, right? But M2 does not simulate M1. So, there's something missing. So M1 simulates M2, but not vice versa. Okay, so we might have to be careful about this. The formal definition, we just went through the matching game of it, but the formal definition, if we want to define our machines in terms of these 5 tuples, where we have the state, set of states, the inputs, the outputs, the update function, right? That's your FSM diagram, but coded up as a function, and an initial state. So these are initial states for S1, M1 and M2. What does all this say? It just says that we build up that simulation relation. M2 is a type refinement, or in other words, M1 simulates M2. If there's a relation where this is our joint space here, such that the initial states are both in there, that's fairly obvious, right? Think about our little examples back here. And now that for all states that are in the simulation space here, the following conditions hold. It seems like a bit of but the key thing here is this little subset containment, if you like, inequality here. So for all I and where, so you put an input into machine 2, it's in a particular state, the update function spits out a new state, that's the next state, right, you've gone to, and gives you an output. Okay, and the same thing happens here. You're in a state in M1, an input comes in, assuming type refinement. The update function gives you the next state. All of that says that both of those states have to belong to the joint state here, right? Remember the simulation relation here? Think about it that way. But the output of machine 2 is only a subset of the output of machine 1. Okay? So output set for machine 2 is contained in output machine 1. Now this is simulation. There's no by in this simulation. It's like a one-way thing. Very important, right? It is, the output set for this is contained in the output set of that. Right? It can just do enough to simulate it. By simulation, all that stuff is exactly the same, all that formal definition. The only difference is equality. Okay? It does exactly both, it goes both ways. An equal sign goes both ways, right? So it goes both ways. Okay. So bisimulation is a stronger form of equivalence between two FSMs. And as I said before, they're bisimilar. So M1 is bisimilar to M2. If they're type equivalent, we always say that. And when you play the game, on each move, either machine can move first and the other machine can match its move and have compatible outputs in both of the machines. Okay? So we played the game for those two machines before. We found it worked one way, but it didn't work with one. So there's a simulation relationship between the two machines. If you play the game both ways again, M1 goes first, M2 goes first, and outputs are all compatible, you get bisimilarity. And what happens is, I'm skipping, sorry, but all the same junk is in there, just that now the outputs are exactly equal, okay? That's what's important. Okay, so obviously we found machines that simulate each other that are not bisimulator. Sorry, we found one that was a simulation but it's not bisimilar. You can actually also get machines that M1 simulates M2, M2 simulates M1, but they are not bisimilar. How so? Well, here's an example here, right? So essentially we have to do the same tracing, right? So we need to pick machines to go first, right? And then toggle through the sequence of states here and all the possibilities here. We won't go through it here, but I'll leave that for you guys to go through because there's a ton of states in this guy here. It seems as though all output sequences are covered, right? 01, 00, 01, 00, 00, 01. But the key is that having to make decisions early does not hurt you unless you exercise it. So this machine here obviously has decisions to go early, and then it has only one decision for these two branches, whereas this one has two decisions here. So I want, as an example, for you guys to go through and play with this and try and come up with a little simulation relation here, like this, and see what the output, if the output is okay. This is only a pure output here, so you're just checking ones and zeros. Okay, so the formal definition of bisimilarity is essentially the same, such that we actually have pure equality here between the two outputs here. So the theorem in terms of language equivalence is that if M1 simulates M2, then we say that the language of M2 is contained in the language of M1. And there was a nice little Venn diagram there before. But it doesn't flip the other way, okay? So if you think of it going this way, the implication is left to right. It doesn't go right to left, okay? So if the language of M2 is contained in the language of M1, it doesn't mean the case that M1 simulates M2. It doesn't go the other way. All right, so here's a neat, handy little summary of all of the things from today's lecture about equivalence and refinements. So each bullet point defines type, language and simulation and bisimulation, and then gives you the definition underneath it. So type refinement was pretty simple. You can replace one machine without causing type conflicts on the inputs-output ports. Language refinement is such that only output sequences, so M2 can only produce output sequences that M1 can produce, given the same input sequences. So remember the little diagram showing the language embedded in another set of language. M2 is a simulation refinement of M1, or equivalent, we say M1 simulates M2, if at every action M2 can produce only outputs that M1 can produce. Now remember, for deterministic state machines, these things are the same, right? And you might already be thinking, well, they sound the same. They are for deterministic machines. We're so used to thinking of deterministic FSMs. But for non-deterministic machines, it depends on who goes first, and then we'll see. Biosimilar means that at every state, either machine can produce only outputs the other can produce. Once again, play the game of who goes first and check the outputs to make sure that they are agreeable. So when we say, is it valid to swap M1 and M2? Then down the bottom here, the meaning of valid once again varies. Is it valid just to bolt it in terms of types, in terms of the language, or in terms of simulation or bisimulation? It's not trivial, okay? And we say that M2 implements M1 here, if M1 is a specification, if M2 is also valid according to these sort of 3 or maybe 4 tick marks here. Okay? Right, so this is enough now in terms of tools for you to go and take 2 FSMs and show that they are valid to be replaceable or equivalent in some sense, okay? I think we'll leave it there for today. Experiment a little bit with this technique. Try it on your friends' FSMs for the Kabuki robot project. Maybe you're doing the same thing. Who knows? All right, we'll leave it there. And we've obviously got the break next week, so I'll see you after the break.